Right. Good afternoon. Sorry. Good evening, everyone. Good evening, guys. Hello, class.
Good evening.
All right. Okay, so thank you. So today we will continue with our unit 3 for signals and systems. Okay, for signal and system, we are going to have system analysis using Laplace transform. We are not going to cover on the Z transform, only until the Laplace transform, I think, in our slide. Okay, so I hope that all of you already has the notes. Previously in our class, we have discussed in tutorial 1. Okay, in tutorial 1, we have covered on the introductions to signal and system. We have learned what is the systems, what is actually the signals, and what are the commonly used signals, the types of used signals, also how to classify the signals. We have signals classifications in terms of the continuous time and also the discrete time signals. And we have also covered on the characteristics of the signals. All right. Rather than that, we have covered on time domain analysis of the system. We have continuous time domain, also the discrete time domain. Okay, that is in unit 1 and unit 2. Okay, we have covered in tutorial 1. Okay, and today we will go for the system analysis using Laplace transform. What is actually the Laplace transform? Okay. Laplace transform. Okay, it is we can use for both continuous time system. It is CTFT, continuous time system frequency transform, and for the Z transform to analyze discrete time system. For the digital signals, is actually a sampling of a continuous time signal for every instance of a time interval. And Laplace transform in terms of engineering. Okay, in the engineering, this will help in transforming the functions, or if we have the waveforms of the signals. Okay, from the time domain to the frequency domain. Okay, that is the primary use of this Laplace transform. Okay, then we also have the Laplace transform, also the inverse Laplace transform. How to write actually for the Laplace transform? It's like L, capital L. Okay, this is the, if we have the frequency, the functions in time, okay, in time domain. Okay, we want to get the functions in frequency domain. Okay, as you guys can see here, this is Laplace transform. It's a type of integral transform from this one, and we can get this is with respect to time domain. Okay, the functions we have in time domain, and we want to get into the frequency domain. Okay, it is to transform the functions in time domain into the frequency domain in the functions of S. Okay, the new functions is a different domain. Okay, basically it is in S domain, frequency domain. We have the Fs is the Laplace transform of the Ft. Ft is in time domain. And this is how to write, okay, the Laplace transform of the frequency. Let's say we have this Ft frequency functions. Okay, this is a normal function. It can be anything. Let's say for x plus y in terms of the variables. Okay, it can be either x, it can be either y, or in terms of the functions f. Okay, and then the domains that we want to convert after apply the Laplace transform will be the S domain. Okay, if we have the ft is equals to 1, so this one we replace in the ft. Okay, for example, if we want to convert the function of 1, okay, from 0 to infinity, we can get this is the original functions from this one, ke minus st with the functions of ft, and for here our ft is equals to 1. Okay, so we can get this over dt. Okay, so just integrate this one and we can get from here 1 over s minus, we have this minus 1 over s e to the functions of t. This is actually how to get, just integrate this one. Okay. Okay, so for the Laplace transform is an example of an improper integral, and this is one of its limits is the infinity limits. Okay, initially is from 0 to infinity, and due to that we have the integral from we set to the h infinity h limit. Okay. And the rest is just carry e to the power of t. This is the functions of f functions. Doesn't matter it is either 1 or t, can be 2t, just replace in this f function. Okay, for example, if we have functions of f t integral from 0 to infinity e to the st f t dt. So if the ft is equals to 1, so just replace this one into here. And then we can get limit. We want to set h into the infinity. From 0 to infinity, e minus st, ft is equals to 1. So we have the dt. Okay, when we set from h into infinity, it is minus 1 over s e minus st from 0 to h. Initially, it is from 0 to infinity, but we replace with the h. Okay. So when we plug in the value, we can get 1 over s. Okay. And for this one, okay, we call it as the unit step because the functions of 1. Okay, unit step functions or the Heaviside function. Okay, this is, we can consider as a switch because it is either true or false, high or low. This is considered as on, this one is considered as off. If it is greater than certain interval or certain value, then it can be on. If we set it is lower than an interval, so it will be 0 and considered as off. So this is for the applications for the switches. Okay, from here this is the applications from 0 to C. This one is off conditions. This is for on. For on condition. Okay, which coincides with the Laplace transform of the function. from the functions f t equals to 1, okay, with from t greater than 0. Okay, with the unit step functions, we are able to determine the Laplace transform of a function that is shifted horizontally. Okay, meaning that it is shift from this point, from the origin to the cutoff point C. Okay, and then it will be at high conditions. This is considered as on for the switch. Okay, so next one we have if the function f is equals to t. Function f is equals to t, and then for the Laplace transform, the Laplace ft is equals to 1 over s squared. Okay, it actually for this Laplace transform, there is table for the Laplace transform. Okay, so you need to know how to apply, and normally the table will be given, okay, during the test or the final exam. Okay, so if the functions is equals to t, so we can have it is 1 over s squared. Okay. Okay, this one is for the switch until at certain point will be off, and then if it is greater than the C, the cut point value at this point, it will be high. Okay. Okay, for this here, we have for the Laplace transform, we have few properties that we can apply. First is in terms of linearity. Okay, it is for A and B functions. And then we have the multiplications. Okay, multiplications by the time. Okay, from the ft, we can get in terms of divisions of fs over the ds. Okay, differentiates over s domain. And then it can be in terms of the complex shift properties. Okay, for the complexity shift properties to get the fs plus a. So it is shifting. Okay, this is to determine either for the shifting properties. Okay, number 4 is time reversal properties. For the time reversal, it is if the functions is in term of minus t, we can get f minus s. Okay. Okay, if in the time domain it is small capital F, capital F, it is upper capital F for the time domain. Okay, and also we have the time reversal. Next one is time scaling. Okay, for time scaling, it is F over, T over A. If we have T over A, so we can have the A, F, S. So as you guys can see, this is T over A in the time domain. If in S domain, it will become a multiplication factor. Okay. And we have the frequency shifting properties. Number 6 is frequency shifting. For the frequency shifting, it is from S, for example, to S dot. Okay, and also number 7, it is the integration properties. Okay, for integrations from 0 to t to integrate. All right, so this is some the properties functions for the Laplace transform. Okay, we can use the Laplace transform to turn an initial values problem. I believe that you guys familiar with these conditions for initial value. Okay, initial value problems, initial conditions. The theorems allows us to obtain Laplace transform of a function with multiplications by the t. And the property can be repeated, applied, and Laplace transform of higher derivative we can obtain. So this one we consider as higher derivative because we have double prime, this is single prime, and this is for y. Okay, for this one we can get, if double prime, meaning that we can get s squared. Okay, for 3y prime it will become plus 3s. This is minus 4. If it is no derivative or no prime, it is minus 4. All right. So this is from there, s squared plus 3s minus 4. This comes from this one. So we can solve for this to get the roots. Okay, there are few conditions for the roots. It is either complex or distinct or unique and distinct or repeated roots. Okay, so from there we can solve once we get the roots. The Laplace transform are particularly effective on differential equations with forcing functions that are piecewise. Okay, like this is sawtooth functions. Okay, so this is considered as a ramp function. All right. So now, once we have, okay, for, for here, this is the initial value problems given. Okay, so once we have this one, if we have this value, so in the solutions, we must replace with the given value. This is, we call it as the initial value problem. Okay, the IVP, initial value problem. So we can get from the IVP, we can get the Laplace transform to get the algebraic equations. Okay, when a phenomenon repeats itself again and again within the some amount of time, it can be represented by what we call it as the periodic function. Okay, what is the sum of the problems of the periodic functions? For example, the motion of spring. Okay, meaning that the spring will be repeated for some amount of time in a certain period. Okay, and also rather than that, this is swinging of a pendulum. Okay, swinging of the pendulum will keep, for example, if we have the pendulum, will keep swinging, okay, to a certain directions, okay, with a some amount of time, in a some period of time. So it will keep swinging, okay, for the pendulum. All right. So if you want to solve for the algebraic equations, from this one, we have numerator and denominator. So for here, this is the one that we can get the roots. Okay, for the Laplace transform is very useful in solving systems of linear differential equations or for the ordinary differential equations. Ordinary differential equation. ODE is ordinary differential equation. Okay, we can find the inverse Laplace transform of the solutions. Okay, for Laplace transform, it is from t to the s. If it is inverse, it is from s to t. Okay. So if we have the table, it is you guys can search around for the table of Laplace transform. Laplace transform table. So we have the time to S domain and also from S domain to the time domain. Okay, from there we can get the solutions of the IVP. Like this one here, it is in terms of S domain. So we want to get the revert from S to the time domain. Okay, inversely, previously we have the initial value problems, we get the Laplace, and then we can get the algebraic equations. But if we have the algebraic equations, we can get the inverse Laplace transform to get the solutions of the IVP. This is in terms of S domain, and then the IVP initial value problems is in the T domain. Normally, the initial value problems will be given the initial condition. Okay, for example, if we have the inverse transform of 1 over S minus E. Okay, if you have the table, then you can see in the table what will be the frequency, the functions in the time domain. Okay, it is actually a, oh sorry, E to the power of T. E is the exponential. This is the functions. Okay, how to write? It is actually, okay, this is to write for inverse. To write for inverse must have this is for Laplace inverse. Okay, from the Fs, okay, we want to get the Ft. Okay, so from the Ft, from this function, this is actually the functions inside here. So we can get the exponential A. Okay. Exponential AT, this is the value. If A is, let's say kalau if 1 over S minus 4. So for here, the A you replace with the 4, the number 4. Okay. Depends on the value given. Okay. All right. So for the inverse Laplace transform can be applied to solve differential equations and also for the simultaneous ordinary differential equation. Okay, we must apply the Laplace transform to ordinary differential equations to obtain algebraic equations. Then we can solve the equations and apply the inverse transform to obtain the solutions for the ODE. Okay, so this is the S functions in S domain. Okay, we have the minus S plus 1, S squared minus ES minus 1. Okay, for the numerator and the denominator. And this is by solving using how to get this one from the first at the top to the equations at the bottom is actually we need to solve by using the partial fractions. I hope that you guys know how to solve using the partial fractions, especially for these equations. Okay, for these equations. Okay, if not, please go and search how to get the partial fractions. There is few formulas for the partial fractions actually. Okay, and for this one, okay, you need to get for the root. Okay, what will be the root for partial for these expressions? Okay, so this will become the solutions to the initial value problems with the, this is actually the shifting properties. It comes from these shifting properties. And this is the initial value problems. Okay, initial value problems. How to get for each of the value this one here, we need to do the partial fraction. Partial, okay, partial fractions. I think in our online lab experiment, we have some assessment to do for these partial fractions. I haven't get the course assessment through yet for the online experiment. Okay. How we can transform a differential equations by using the property of Laplace transform. we need to have the properties of Laplace transform like I have informed earlier. Okay, and first for the Laplace transform and inverse transform, it is considered as linear function. Okay, if we have the ft, gt, and other functions with the Laplace transform, then if we have the a, ft, for example, here we have the c, we have the cft. So from the c, we can take out this one. So we can separate into these two. This is the first function, and this is the second functions for the gt. Okay, so for the inverse Laplace, it can be for the c with respect to the f functions here, and this is for inverse Laplace of the g function. Okay, and we call this constant value, doesn't matter it is either c or a or b or any value, it is considered as the arbitrary constant, all right, with respect to each function. Okay, there are very simple relationship between the Laplace transform of a given functions and the Laplace transform of a function's derivative. So this one also we can relate with the initial value problems. For the property can be repeatedly applied and the Laplace transform of higher derivative we can obtain. This is the initial conditions. How to determine on the initial conditions? It is actually, for example, this is at time from this is actually okay, 0 is at time equals to 0, and if this one it is actually from at at f prime t. Okay, let's say for here is we put it 0, this one is 1. So in the function, for example this one, so we must replace with 1. Okay, if it is 0, so we replace with 0 according to the value given in the initial value problems. Okay, and one more thing, it is a transform of derivative. Okay, this is we call as the transform of derivative. This is the first derivative. Okay, this is the first derivative, the upper one. This is the second derivative. How to determine the first or second derivative? It can be also the third derivative actually, but then I think in our syllabus we only cover for first and second derivative. Okay, how to determine? You must look and observe here. This is for first derivative, meaning that derivative is dt over dx. For example, this is for dt square over d x squared. Okay, for this is for second derivative, this is first derivative. For first derivative, we look at the first derivative firstly. Okay, we have the s. How to transform? We have the s. This is the functions of ft minus the initial condition. Okay, minus the initial conditions of the f not given. Okay, must be given. Normally, dia akan bagilah the initial condition value. Right. For the secondly, this is for second derivative, we have two double prime here. Okay, two double prime here. So, how to get the expressions for the second derivative? It is s squared. Okay, s squared, this one is just follow the same as previously as the inverse Laplace functions of the ft minus f initial given, okay, f naught. So must have this f. And the next one minus f prime x naught. So if it is given f naught and f prime naught, this one must be second derivative order. Okay, for second derivative order. So these two is the theorems of the Laplace transform derivative. Okay, transform of the first derivative and second derivative. Okay. Kena ingat ke? Yes, these two you need to memorize and understand how to apply for these two Laplace transform functions derivative. Okay, the Laplace transform for derivative is very useful in solving linear differential equations, since by observing the properties, we can see that derivative are polynomial because we have the s squared. Okay, so first thing you must write the whole derivative. It is either first derivative or second derivative. Okay. Okay, so next we go for, we know the rules that let us determine on the Laplace transform, and also we have the initial value problems. Okay, and the Laplace transform for derivative is useful. We can get the polynomial in S. And then for next one, we go for to apply on the Laplace transform to solve differential equations and the simultaneous ordinary differential equations. We need to apply the Laplace transform to the ODE to obtain the algebraic equations in terms of the T, and then we can solve the equations. We apply the inverse Laplace plus the Laplace transform to obtain the solutions for the ordinary differential equation. Okay, there are two ways. It is either by using the convolution theorem, or the residue theorem. Okay, we must know the Laplace transform. Okay, and then this is how to write for the Laplace transform. We can get in terms of functions f or in terms of functions g. Okay, and then we know that since this is t, that is why it is continuous signals. Okay, meaning that the Laplace transform are invertible. We can get from the t time domain to the frequency domain and Laplace domain representation. And the other things that you need to know for the Laplace is the partial fractions knowledge. I think this one you already learned in maths or in control engineering subject. Okay, so this is for inverse Laplace transform. We can get from the time domain into the S domain, or if it is inverse Laplace from S domain to the time domain. Actually, if we have the Laplace transform table, it can be, the table is in time domain. You guys can search. Previously, we have the table in notes, but for this new notes, we don't have. I'm not sure why. Okay. Okay, because I've teach this subject, I think 3 to 4 years back. Okay, that one we have the notes. Okay, for example here, we have the functions of delta t, and then if it is delta t for S domain, it is equals to 1. Okay, if it is unit step functions, it is 1 over S. Okay, else if it is t, here if it is t, it is 1 over S squared in the S domain. So if you want to solve, you can straight away refer to the Laplace transform table. Okay, there are few more properties in the transform table. Okay, and when we use the Laplace transform to solve differential equations, the solutions are functions of the Laplace transform variables and rather than of the time variable of t. Okay, and Laplace transform is an improper control integral. We need a creature from the world of the complex variable. Okay, but all the real-time signal that we are concerned with are in time domain. So the final form should also be in time domain normally lah. Okay, therefore, a method for converting function s back to the function t called inverse Laplace transform. Okay, using the table, and also we can use the algebraic system. Okay, just skip this one. Okay, for example, if we have the XS, we have the QS and the PS. Okay, this is denominator and numerator. For rational Laplace transform, the roots of the numerator polynomial are called the zeros. Okay, the zeros and the poles. Okay, the roots of denominator, this one, we call it as the poles of the XS. Okay, and we have the simple pole. For the roots, simple pole, or it can be complex poles. It can also be a repeated pole. For complex, normally involved with the imaginary number. Okay, and it can be unique and distinct pole. Okay, the inverse Laplace transform convert the functions at xs into xt, and then we can denote and write in terms of xt Laplace inverse of xs. Normally this is huruf kecil, this is huruf besar ya, for time and the for s domain. And from there we can get in terms of for the xs, this is like previous, we can have the denominator and numerator. Most commonly found form of the Laplace transform in engineering. Normally when we solve, kita akan dapat dua lah. Satu dekat atas and then satu dekat bawah. It will be the numerator and denominator. Okay, we call it as the zeros and poles. Alright, next one we go to the impulse. Impulse is the effect of the force that acts over a very short time of interval. And engineers and physicists use the direct delta functions. What is that? Okay, this one. Okay. And direct delta functions, or normally we write as this one. Okay, is mathematical functions with special properties used in engineering, physics, and also in the signal processing. It is not a conventional functions, but rather a generalized functions, or it is the distribution function. Okay, we go deeper into the direct delta function, call this as the quasi-functions. Quasi-function was created by the PM for the inventor of quantum mechanics. Okay, and properties of the direct delta functions, we have few properties. Singularity of the zero, singularity, oh, okay, singularity of zero. Okay, we have the zero for all x is not equals to zero. So this one we call it as the singularity of zeros. And then we also have the shifting properties. Okay, second is shifting. Okay, shifting properties for sampling. This is actually for sampling properties. Okay, and also we can apply in the integral properties, derivative relationship, and also for the Fourier transform. Okay, for that, normally we can write in terms of minus infinity to infinity. We have the functions of fx for the direct delta. x minus a. We have the constant value a here shifting. Okay, shifting over the dx. Oh, okay, over dx. Okay, we can get the f a. So this is for the shifting properties. We can apply in the integral properties, derivative relationship, also in the Fourier transform. Okay, this is as the shifting properties. Okay, we also have the applications. The applications for the direct delta functions is in terms of electrical engineering signals in circuit for the model impulse, and also can apply in the control systems where we use to analyze impulse response, and also we can use in signal processing where we can represent the ideal sampling. Also, for the in terms of physics, for models, point charges, and also masses and Green's functions in differential equations. Okay, but beware that in some contexts, especially when dealing with purely numerical simulations or when a system is better analyzed in the time or frequency domain, we have limited appeal for the Laplace transform. Okay, we cannot use to find general solutions to a differential equations, and also cannot use on initial value problems with initial conditions in the different forms of values. Okay. However, for Laplace transform remain useful in normally when we apply for control system. Okay, for example, if we want to do the stability analysis. Okay, also when we want to apply for circuit analysis, we want to get the transient response of, let's say we have a circuit. The circuit contain on the RLC components, resistor, inductor, and capacitors component. So we want to get on the transient response. So we can use this Laplace transform. Other than that, okay, for this one, the conditions must be initial conditions at a point other than 0 will not do. So must have the value of the initial conditions at a 0. Okay, this is just now, like I've mentioned, we have the RLCL. RCL is for inductor, R is for resistor, C is capacitor circuit. Okay, we can apply. Normally for this one, we have in control engineering or process control. Okay, and also we can apply in differential equations where we want to solve on ordinary differential equations with initial conditions. Okay, so if the initial conditions is given, so we can apply for this Laplace transform. Okay, what do we expect to be able to do? For system realizations, normally we can apply for this Laplace transform. Let's say we have a system. So for one system, there must be an output. For that one, we need a input. Okay, so we have X is the input, this is the system, and this is the output. Okay, a block diagram, this is considered as a block diagram representations of an input-output relationship. Okay, so for the HS is the system. Okay, for the whole system, and then we want to get the input to the output for the signals transfer. Okay. Okay, and this is the definitions of the Laplace transform. Also, for the what actually you need to know for the Laplace transform. It is what is actually the Laplace transform. And then for the Laplace transform, it has few properties. You need to know what are the properties. Okay, and then for the Laplace transform, we can get from the xt or the ft. We want to get into xs. It is actually two-way substitutions from the time domain into S domain. You can also get from the S domain into the time domain. So we have the inverse Laplace transform. Okay, and then for the properties, we have the linearity. For the time shifting, we have the frequency shifting. Actually, we can relate with the properties of the function. Sorry, properties of the signals. Okay, we have the initial and final value problems, initial and final values that we need to apply, and also time differentials and the time integrations. Okay, and we need to know where we can apply and why we cannot apply. For certain conditions, it cannot be applied. Okay, and before we end, the SS, normally the functions is commonly expressed as a returnal functions. Hence, it is convenient to use the method of partial fractions expansion. Okay, and the table of transform pairs is obtaining for the inverse transform. So from the Laplace, we can get the Laplace. Also, we can get the inverse Laplace. Okay. So actually this is all for the notes in slides unit 3. Okay. I want to stop sharing and I want to stop recording. Do you have any question from you guys? Any question?